Hi James, how are you?
Very good. How about yourself?
Great, I'm fine. Can you describe your job at Intel?
I think I have the greatest job in the world. I go out and tell people about what I'm passionate about, which is parallel programming. I've been doing that for decades. Now we have multi-core, so many people are interested in that. And I take what I hear, what customers tell me, and I get to meet with a lot of interesting people doing multi-core development, and I take that back to Intel and help be part of the team that discusses what products we're going to create, what to do with that customer feedback, and then I go out on the road again and talk to customers, and I do that over and over all year long.
And you make feedback on the development team?
Absolutely,
to add some feature or to provide a new idea?
Oh yeah, absolutely. To add features, to find out what we're doing right, what we're doing wrong. Just picking something like Intel threading building blocks, I get to hear a lot of feedback about, well, you got all this right, but it doesn't work in my program because I need this other feature. And I think we're very responsive to that, but it's to me that's very enjoyable to find out how our products are working in the real world.
Okay, great. Can you explain why Intel provide a new CT compiler, and if you can detail how it works and the integration with RapidMine technology, and maybe have a look at integration with a Larabi processor. Maybe there is some correlation. If you can explain.
Absolutely. So I'll back up a little bit. It's when we started looking at multi-core parallelism, I'd say that the most predominant way of doing parallelism was to call out to Windows threads, or if you're on Linux, to P threads, and that's too low level. So the first thing we worry about is give me a good abstraction. So when you do your first abstractions, you want to do something pretty general purpose because you want everyone to be able to use it. So you look at things like OpenMP that Intel and Microsoft both support. You look at doing a tasking oriented task stealing system like Intel threading building blocks, or now Microsoft's PPL and TPL. Those are very general purpose. Now that we have those, we have an opportunity, and that is to go develop things that are more specific, less general purpose, but maybe better at their job when they apply. CT is exactly that. It's not really a compiler as much as it is extensions. It's actually going to be template library extensions in C++, at least the first implementation. It's focused on data parallelism. So the thing that we are able to do with data parallelism that, say, TBB can't do is we get more control over the data structure. So the way that a developer will describe their data will allow CT to take control of that, understand the operations on the data, and then move it between CPUs, even distributed memory, maybe off to a Larabi or to an NVIDIA GPU. But because we have the control over the data, we can move it around and we can reorder operations on it. And that's really what CT is about being able to express a data parallel problem, but have enough control over the data to ship it off to an attached processor if that happens to be what's on the machine. Now we couple that with a bit of jitting technology so that we don't actually compile to the target machine at compile time. Mm-hmm. We create an abstract explanation of what we want to accomplish, but then at runtime we can take a look at the hardware we're on. If it's a 16-core machine, we'll use 16 cores. If it's a 4-core machine, 4 cores. If it's a quad-core with an attached GPU, send it off to the GPU or share it between the quad-core and the GPU. That happens at runtime.
Okay, it's great. It's very similar of Java or .NET because we compile the code, but during the runtime there is something that recompile some part of the...
Yes.
Okay. And the decision between GPU and CPU is made by the developer or just by the runtime?
The runtime.
The runtime.
Right, because the capabilities of the GPU, or if it's an attached processor like a Larabi or something like that, they're going to vary, and the runtime will make the decision based on the calculation it's trying to do, whether moving the data makes sense. Also, data movement's a big issue. If you've moved data off the CPU to another processor, even if it's less efficient to do the next step of processing, you might want to leave it there before you bring it back because you understand the data movement. So that complexity is taken away from the developer, and we just are left with very mathematical notation like A equals B times C at the high level.
Okay.